probably the main reason for the current enthusiasm around machine learning and AI, I would say, is the ever-increasing availability of data. And what I'm interested in is extracting knowledge and meaningful hypotheses from bigger and bigger data sets. Hypotheses such as this one up here, which is the title of my talk, Are Nurses the Real Heroes? So let me put first things first and start by introducing the data. All right. So for the first data set, I would like to introduce individuals in a hospital ward were asked to wear proximity sensors for a week. And these individuals include patients and doctors, but also nurses and administrative staff. And measurements of proximity were taken in time windows of 20 seconds. So for every time window, we have a matrix. And whenever two individuals interact, that is recorded as a 1 in the matrix at the corresponding coordinate in the matrix. So we have thousands and thousands of binary matrices of size number individuals by number of individuals. And we can now stack these matrices. And what we get is a three-dimensional tensor that records around 80,000 interactions. So again, the question is, how can we get insights about what's going on in the hospital from this tensor? Before I go to the answer, I'd like to introduce a second data set just to show some more challenging example here. Here we have observations of gene expression of around 1,000 genes in the tumor tissue of cancer patients. So for those who are not familiar with genetics, here's a very coarse-grained explanation of what that means. So there are around 20,000 genes in the human genome, and there are building plans for proteins, which are the basic functional units in the cell. And today we can measure how active each gene, each single one, is expressed in a given cell. And that's a very essential characteristic of each cell. Importantly, though, the absolute level of expression can actually be quite misleading because some cells are simply expressing many more genes than others. So instead, what we look at here is for each pair of gene, A and B, we draw a black dot, a 1, whenever a gene is more expressed than gene B, and a white dot otherwise. So we have a 1,000 by 1,000 array of ones and zeros for every patient. But now we have 7,000 patients. So this leaves us with more than 7 billion data points. And again, the question, how can we get to interpretable insights and hypotheses from such data sets? So to this end, I'm working on latent variable models that are interpretable and that can quantify uncertainty and that are able to scale to massive data sets like this. And in particular, they should have a reasonable correspondence to the data generating process such that they can uncover the latent causes that have generated the data. So how can we model latent causes of binary outcomes? Let's consider an example here. Say we observe a certain disease in a population, and possible causes include obesity, smoking, exercise or the lack thereof, and genetics. So what conventional models do is they attempt to explain the occurrence of disease in the population by an interplay of all these factors, such that you have disease is caused by obesity and smoking and the lack of exercise and the genetics. So this might be true in the general population, but we all know that person that becomes 100 years old even though they smoke all day, or the super fit person that gets ill at young age. So for any individual, only a single factor may actually be required to trigger the outcome. And, oops, what happened here? The logic we would like to apply is actually that the cause of the disease is obesity or smoking or exercise or the genetics. If we now go to the case where we measure multiple outcomes across multiple patients, this OR logic can be formalized as the Boolean matrix product. So this is a product between two binary matrices, Z and U. And the first matrix, Z, indicates the presence of or absence of the causes in each individual. And the second matrix indicates the presence or absence of any observable feature for each of the causes. And the Boolean matrix product applies a conjunction that is an AND operation across the indicators and the features. And then we take the Boolean disjunction, the OR operation, across all causes. So this might be a bit abstract. So a more informal representation would say our X and Ds, our outcomes, indicate symptoms in patients. And the patient has a symptom if there's any latent condition that applies to the patient. And this condition is also associated to that symptom. And when I say any, that's where the OR is encoded. And that the condition has to apply to the symptom and the patient, that's the AND. So our ultimate goal is to actually do the inverse, to go from observed symptoms to the latent causes, that is the conditions and the diseases. Before we consider the problem of inferring these, we can actually simulate data under this logic. So let's just draw two binary random matrices. The first one indicates patients and conditions, and the second one indicates symptoms across patients. And then as a result of the Boolean product, we just get this binary matrix on the right. So I'm showing you this to make another interesting point, which is that the binary data that we work with here denotes exclusive categories and is fundamentally different from continuous data. So if you say it's a 0 and a 1, or it's a -1 and a 1, that has no correspondence to the actual numerical value. However, people still commonly use models for continuous data like PCA to analyze this type of data. So here's an example of what happens if we use principal component analysis to analyze this randomly generated data that follows our Boolean product. The zeros here encode the false entries in white, and the black dots are the ones which are true entries. So we can see the 4 latent dimensions from PCA, and they actually reconstruct the data up to 95% accuracy, but they don't really show any of the binary pattern, the logic pattern that has generated the data. So they're not very helpful in achieving our goal. So what we do instead, okay, I don't want to be too technical here about what we do instead. We construct a probabilistic model for this Boolean product with a simple Bernoulli noise model. And then we're able to go ahead and start the machinery of posterior inference and learn the latent factors. So let me skip this. To be more concrete, what we do is Gibbs sampling of those latent causes. That is, we consecutively update each variable, drawing from its probability distribution conditional on the current state of all the other variables and the observables. And without too much technicalities, there's one reason why this is particularly challenging in this type of model, and in fact in any matrix factorization model. And this has to do with one of the fundamental patterns of cause and effect relationships, which is known as collider bias, or explaining away. So let me try to give some intuition here. Explaining away plays a role whenever you have an observation that can be explained by a number of different causes. Say, for instance, you observe an alarm in your house, and assume that this has 2 possible causes. An earthquake might have caused the alarm, or a burglary. If we draw the causal diagram of that, we get this V structure here. And although earthquakes and burglaries seem to be completely independent, they do become correlated once we make the observation that there's an alarm. So say you hear the alarm and you know that there's an earthquake, then the event of a burglary becomes less likely. So these otherwise independent things become correlated once we observe their common effect. For another maybe more interesting example, you can think of a celebrity, and they can be famous for 2 reasons. Say, either they're pretty or they're talented. And then the catchy narrative is, if the celebrity is really good looking, then you probably think, or you have less reason to believe that they are talented. However that may be, the important bit is that otherwise independent causes become correlated. And if we now go back to our matrix factorization model where we have n observations, d attributes, and l hidden causes, and we draw the graphical dependencies for that model, we have these two drawings. They are just two ways of showing the same thing, actually. And we see that both of them exhibit a different V-structure, so exactly the thing we've seen before. So all the latent variables in our model actually become correlated in that way. So if we want to do inference for a single variable, we need to compute the effect that the change of that variable has on explaining the data. And for that, we need to take into account all the other possible causes. And the technical term for all these other possible causes is the Markov blanket of our variable. So the fact that for each variable we need to do that makes it extremely challenging to scale these type of models. However, the crucial trick is that because these dependencies follow these OR and AND logics, they can represent it in a really, really simple form. Say we're interested in updating a variable z conditional on all other variables, then we need to take the sum and this product over the other causes. But because we have this OR operation, we get this term here in red, which actually says if there's any other cause that explains the observation, the whole expression goes to 0. And similar for the other dependency. So what we need to do in the end is we just need to check for any of these conditions here. Is there any other cause, or is the cause actually causing that effect? So this makes the posterior computation really, really quick and allows us to scale to massive data sets. So we're now almost at the point where we can solve the problem that I've started with. So far, we have considered two-dimensional examples, such as data of patients and symptoms. However, the very same principles apply to data of higher arity, that is data that describes the binary relationship between more than two objects, such as does person A interact with person B at time t? Or is gene Y more expressed than gene Z in patient X? And instead of inferring two-factor matrices in these examples, we infer three matrices that explain the data. But the general logical structure doesn't change. So let's start with our tensor of relative gene expression across 7,000 cancer patients. We can run inference for these billions of data points on standard hardware, and we infer three latent factor matrices. Two of them denote sets of genes with a certain relative gene expression, and the third indicates sets of patients that exhibit these particular expression patterns. So here we see the patient-specific matrix, and each column corresponds to 1 out of 7,000 patients, and each row is one of the latent causes. And we also have some additional information, which wasn't used in the algorithm. For each patient, we know the type of cancer that they're having. So it's 18 different types of diseases, actually. And we order the patient by that. So the columns are ordered by cancer type. It's denoted down there on the x-axis. And we can see that there's a really strong cancer-specific pattern in the data that we pick up with our representations. But at the same time, there's a strong heterogeneity as well, where certain factors, certain rows, appear across different cancer types. So biologists can now make immediate use of that and confirm existing knowledge or discover new patterns of gene expression and generate new scientific hypotheses based on these. And we actually can also use these features to build a classifier that predicts the cancer type. And this gives us an accuracy of 91%. And I tell you that because if we do the same thing for principal component analysis, just for comparison, here's what the corresponding representation looks like. And that's on the continuous data, which is supposed to actually have more information. And the simple cancer type specific pattern that we had essentially disappeared or was only very vaguely noticeable. And moreover, if we train a classifier on that, we only get 86% classification accuracy. So if you stop listening after my first slide, now's the time to join back in. Remember the tensor of temporal interactions in the hospital ward. We can similarly decompose this into clusters of individuals that strongly interact during certain hours of the day. So on the left-hand side, we see temporal activity average to provide us a typical daily pattern. Right? So you have the hours of the day on the y-axis and the 7 patterns that we discovered on the x-axis. And the corresponding groups of individuals are shown on the right-hand side. So each row is an individual, and they're sorted by administrative staff, medical doctors, nurses, and patients. So the first observation there is that there's very little consistent interaction with the patients. And I'd also like to highlight a few other results. In the dimensions 1 and 2, we have interactions between all admin, medical, and nursing staff, and that takes place between 10 and 12, and between 3 and 5 in the afternoon, respectively. So I would assume that's just like the core work hours. And in dimension 4, which I particularly like, this is from 2 to 3 in the afternoon, and includes almost all nurses and admin staff. So I suspect it's just a regular team meeting, or maybe more likely an afternoon coffee break. There are quite a few more examples to read off here, but I'd like to finish with dimension 7, which almost exclusively describes nurses, and strikingly is the only group that consistently active during night hours, from 7 in the evening to 7 in the morning. So maybe nurses are the real heroes. How am I doing time-wise? So yeah, I quickly like to conclude that we have developed a model to discover causes and interactions in binary data of arbitrary arity. So the examples I've shown are tensors, so three-dimensional data, and that the resulting representations are highly interpretable, and we can actually scale probabilistic inference by exploiting these logical dependencies to really large data sets. It's also trivially parallelizable. And we have shown these two examples where it discovers disease-specific latent gene activity in cancer patients and recovers work patterns of different staff groups in a hospital from proximity data alone. And I would also like to acknowledge my supervisors, Chris Yao and Chris Holmes, and my funding sources, which is Roche and the EPSRC, which should be on there, and also, of course, the Alan Turing Institute. Thank you.